Well, hi and welcome to my shop. Thanks so much for joining me here. I'm getting ready to do some very careful and serious tube testing on this radio. But first, just like the last few videos, I'm going to take a moment to show you some information about the thing that's going on in the world. And the reason I'm doing this is I'm just trying to share what I found on my own little poking around on the internet and what I think are probably pretty good sources to keep an eye on. This one's a little different. This one will leave you feeling a little bit better about things, I think. So this is a news story, quite current, April 13th. Today is the 13th, so this is really current. Canadian at work on COVID, whoops, I said the word, 19 vaccine is optimistic. There he is. I'm going to read right through this. I know our vaccine is safe, therefore I will stick out my arm as the first vaccinee, says the doctor who's developed it. The team is using its well-established vesicular stomatitis virus-based technology or whatever. So he's very optimistic about having a preventative vaccine for testing soon, really soon, as in it may be being tested in just weeks on people. 12 hours a day they're working. Now there's another article here, maybe this one doesn't say it. Vaccines need to be safe no matter how effective the vaccine is. If it isn't safe, we can't use it. Ideally, we want a vaccine to prevent over 90% of infection. That would pretty much end it right there. Kang says in the near future he's going to need much more support for the human clinical trials. There's another article about the same stuff that says this isn't the only vaccine. There's another 20 behind it. Potential candidates here in Canada. Now Canada is just a relatively small country. This is going on in countries all over the world. Who is going to find the 90% vaccine? Somebody's going to find it, and they're going to find it fast. So I think that's extremely optimistic stuff to see that these things are real. They're not just people talking about maybe we should work up a vaccine. It's here. It exists. It's ready for testing. Okay, now let's go look at that radio. So I have done a little bit of research on this radio. There's not much to find out about it. The manufacturer of it was a little bit obscure, a small company rather. They went out of business in 1938, I think. The Depression caught up with them finally. This might have been some of the last radios they ever made, right here. There's no schematics available. Apparently they were never published, never got into any public archives that exist today. So conceivably there just is no schematic for this radio. That makes it really, really challenging for me. This radio has a lot of tubes in it. 1, 2, 3, 4, 6 tubes in it. It's a little complicated. Someone else has done work on it already. All these things send off a few red flags. But it is so fantastic looking, I am not going to quit because it's going to be difficult. I'm going to keep working at it. So I think the next stage will be tube testing. That's why I got the tube tester out here. And in particular, what I'm interested in these tubes, these are so old, these are from the I was going to say they're from the 1930s, but probably most of these have been replaced. And so they're probably actually a little newer than that. But regardless, this is it's a pretty old radio. And so the tubes may have gas in them. So that's what I want to talk about a little bit, about gas in tubes. And not that I'm an expert on this. I'm trying to raise my level of expertise today, in fact. You know, I like learning about things when I have the actual real problem in front of me. You know, learning about them kind of theoretical or just reading about it, you know, it feels great. But have you ever had that experience where somebody explains how to do something and you go, great, let me give it a try, and you sit down in the seat and your hands go out and you don't know the first thing to do? And that's why I like learning by doing, because I find it's much more effective. So what we're going to do here is we're going to pick one of these tubes. We're going to set the tube tester up. We're going to run the regular GM test on it, mutual conductance test. See what the value is. We're going to run the gas test on it at the same time or right afterwards and see if there's an indication of gas. Then if there is an indication of gas in the tube, and by the way, I've seldom done these tests, never ever found a tube to be gassy. But if there is gas in the tube, we'll then let the tube operate, just sit here in the tube tester for a few hours and test it again, and see if the gas gets consumed by the getter in the tube. So which one should we start with? Why don't we start with the great big one here? Let's start with the great big one. I think this one may actually be a rectifier tube, and we can't do a gas test in a rectifier tube. Yeah, this is the rectifier tube. Or is it? Number 43. I think that's a really rare tube. I like that 6-pin tube. 43. Let's find out a little bit about it here. 43. Yeah, these are old tubes, no doubt about it. 43 is the original. It's the original numbering system. You know, tube number 1, tube number 2, and on up to 43. So I believe before they started getting this crazy way of noting tubes. Jim, 43. Think, man. Think. Sometimes it's hard for me to think and talk. Either one. Either one's hard. Excuse me. Here we come. 43. Power pentode. So it's the output tube. It's a pentode. Glass type used in audio output stage. AC/DC receivers. Tube requires 6 contact socket. Heater volts 25. 300 milliamps. This type's electrically identical to the 25A6. Type 43 is used principally for renewal purposes. So that's a renewal tube. Pentode. Not a power, the kind where they funnel the electrons. I forgot the name of it. Okay, 43. Let me get this set up on a 43 here, and we'll see what we get. Okay, let's take a look at the instructions in the manual here. Testing for gas current. Now notice it doesn't say testing for gas. It says testing for gas current. And of course, you have to have a current to have it, show up on the meter and things like that. Excuse me. So you're not really. It must be the COVID getting me here. You don't actually test for the gas directly. It's indirectly. Let's just see what it says here. Gas current is actually a reverse current through the tube. It is particularly noticeable when the grid of the tube is biased highly negatively. Gas ions then flow to the grid, causing it to become less negative. And below it gives the steps for doing the test. So let's talk about this gas. Where's this gas coming from? The gas is mostly coming out of the materials that are inside the tube. Some of the materials, there could be, I'm looking at the tube here, occasionally you can see mica in there, you can see other materials, who knows what they are exactly, and some of these materials can give off gas, and the gas is just going to fill the vacuum or move into the general space inside the tube and sit in there. And that in itself isn't really a problem, unless it's chock full of air. If the glass envelope cracks and it's full of air, it's not going to work. But a little bit of gas. But what it does is, as soon as you apply a voltage on the plate and start accelerating electrons through this gas, some of the electrons will strike the gas molecules and ionize them. And then the ionized molecule now has a positive charge because the electron's been knocked off and it's probably joined in the flow on its way to the plate. So the ion is repelled from the plate because it's positive, and it would be attracted to any negative terminal that might be in the tube, and that would be the grid. And so now you have ions flowing to the grid. When they reach the grid, they can pick up an electron off the grid and make themselves happier, become neutral gas molecules once again, and they can draw electrons off the grid, giving a grid current. So that grid current is the indication of gas in the tube. And that's what you're really trying to detect, is this current in the grid due to ionic gas flow or gas. So let's read what it says in the rest of the test here. This was a really big problem in early tubes, but as tubes got developed, designers and manufacturers got smarter about what materials they put inside and stuff like that. So And the getter, I understood up until recently, the getter that was put in the tube was there to collect the gas that was in the tube at the end of the manufacturing process. So my thinking about that was once the gas has been drawn out of the tube and is fixed onto the getter, then that problem's over and that's the end of that. But in fact, the getter continues to collect gas molecules for the life of the tube as long as the getter is hot enough. In normal room temperature, it's ineffective. So that's another thing. What I'm doing here is I'm putting these old tubes in to the tube tester. I'm going to heat them up. When I heat them up, the getter inside will become active and start eliminating the gas. So I think. I don't know if that's really true. That's what I'm going to try to find out today. And over time, the amount of gas ions in the tube will decrease. So let's see what it says here. To check the average tube for gas. To check the average tube. What are they talking about there? I know later they say you can't do this unless there's a grid in the tube, so you can't do it with a rectifier tube. Average tube. Okay, maybe there's some more stuff down below that explains that. Check the average tube for gas. Period. Why did they put a period there? Why did they capitalize gas? Set it. Well, that would be a comma there, wouldn't it? Set it for the GM test, and then proceed as follows. Only applies to grid-controlled tubes. Rotate the screen grid voltage to switch A. This lowers the screen voltage. Set the bias slide switch to 50. Meter switch to test. Adjust the bias potentiometer till the meter just barely reads on the scale about a quarter to a half inch from the zero is about right. Push the gas switch. If the meter moves more than a 1/16 of an inch upward, the tube has gas present. Since gas on occasion is not detectable until the tube is well heated, it is suggested that suspected tubes be allowed to operate for several minutes before testing. Gas is particularly troublesome in high impedance amplifiers, AVC, AFC, and television circuits. Gas in a tube causes a grid current. Excuse me, and causes grid bias problems. Okay, well, I think that's the instructions. Let's see if we can pull this off. Okay, let's set up the tester here for the 43. So 25 volts. I've already set that. EGG. Oh, make sure I look at it right. CGGG. So C, G, G, and G. And a dash, so this control doesn't have to be set. And 64312. 6, 4, 3, 1, 2, 5, 50,000 rather. 5, 0, 0, 0, 0. I'm looking at the right one now. That was 43, yes. 13.8 volts bias. And then we have a 1475 is the GM reading. If you look way over on the right side of the chart, you'll see GM and EM. There's two test setups for this tube. That's what makes this tube tester special. It does both EM and GM tests, and on some tubes it'll suggest one of the tests is more critical than the other. And in this case, and it's almost always the GM test, but not in this case. You can see the little asterisk beside the EM indication. What it's trying to say here is the EM test is more effective at judging this tube. But the gas test is done with the GM settings. Okay, so we'll complete the test here. Put the tube into the 6-pin socket rather. Looks like this one. Fat ones here. What's with this? It's just really hard to put in there. Probably very few tubes have probably been tested in that socket. That's probably why it was so tough. 43, 25, we're ready to go. On. Gonna have to put this here. What this switch said here the heater is turned off on the tube. So the heater will not be running in there. And first thing we're going to do is a short test. Rotate through here. Now two of them, the ones, when it's on 1 or 6, you should see a short. Starting with 10, 9, 8 is how we're going. 10, 9, 8, 7, 6. So there's the short. 5, 4, 3, 2, 1. Blast off. Okay, so now we're heating the tube. Now we want to set the bias on the tube. Here's the bias control setting. Flip this to bias. The meter's now reading bias. It's on the 10 volt scale. The bias is supposed to be, where to go there? 43, 13.8. So we need to be on the 50 volt scale. Well, that hardly moved. Plenty fishy there. My gosh. Well, that should be a factor of 10 to 50, factor of 5, the meter. Something funny going on there. Okay, so we'll do what we're supposed to do anyway. 13.8. That's a funny number. So on the 50 volt scale, 13.8 is going to be right around there. And the tube is glowing mightily over here. So we now have the right bias. We'll check the line voltage. Just a touch high. Just knock it back a little bit. Bias. Still at 13. We're in the test mode. Now we'll check for current flow. So it's supposed to be 300 milliamps at the full scale here. Oh, so my meter won't go full scale. It sticks, unfortunately, but it was certainly on its way up there. On the 3 amp scale, this is reading, yeah, it's very, it's not even worth looking at. 0.4 is what it's reading, but I don't think that's going to be reliable. There we go. Now we're ready for the test. The test result should be on the 43, 1475 on the GM test. So 1475. Now the scale we're looking at is scale C, which is the 8K scale. 8K scale is the numbers under this line. So what's that number again? 1475. Well, I would make it down here somewhere. Right around here. There we go. With the test. Right around there. So this is passing the test, the main test. Now we're going to do the gas test, and I better get the instructions up here. Gas test instructions. Okay. Gas test instructions. Testing for gas current. Gas current, reverse current is particularly noticeable, blah, blah, blah. Check. Set it for the GM test and then proceed as follows. Rotate screen voltage switch to A. Rotate screen voltage switch to A. This lowers the screen voltage. Set bias slide switch to 50. Meter switch to test. Adjust bias potentiometer until meter just barely reads on the scale. Adjust bias until bias. So it just barely reads on the scale. So we're saying 1/4 inch to 1/2 inch, so that looks pretty good like that. Put it right there. Okay. Adjust bias potentiometer barely reads up and push gas switch. If meter moves more than 1/4 inch upwards, tube has gas. Gas switch. Gas switch. There it is up here. Gas switch. Okay, so watch the meter very carefully as you can from that distance. No movement whatsoever. It's so not moving. I don't even think it's working. Is this really working? don't see the slightest move. Test. Oh, we're not in test. Duh. Put it in test mode. Now wait a minute, is that, wait a minute. Let's go back and read the instructions here. Adjust the bias potentiometer until meter just barely reads upscale. Maybe you're supposed to do it in test mode and adjust the bias to get the, oh, it has to be under test. Ooh, am I doing this right? Let's read this again. Set it for the GM test, then proceed as follows. Rotate screen to A, lower screen voltage, set bias slide 50. Meter switch to test. Yes, what I did. Meter switch to test. Adjust bias potentiometer until meter just barely reads. So it doesn't say, it says meter switch to test, and then it says adjust bias. Barely reads on the scale. Okay, so I didn't do it right. So we put it on test. Well, this meter can't go anywhere till this is on test. I don't think. Okay, let's try that. What happens if I go like this, and then I adjust this just down so it's just barely above? And put this on hold. Test hold. Now we do the gas test. Still no movement whatsoever. Have we done this right? Let me go through it again. Rotate screen voltage to A. Set bias slide switch to 50. Meter switch to test. Adjust bias potentiometer until meter just barely reads. I'm adjusting the bias, yeah. 1/4 inch from the 0 is about right. Push gas switch. If meter moves more than upwards, gas present. Since gas on occasion not detectable until tube is well heated, it's suggested a suspected tube be allowed to operate for several minutes. High impedance amplifiers ABC. So this is actually, I think you would call this a low impedance amplifier. I'm not sure though. It's just not moving at all. So, you know, the conclusion is there's no gas in the tube. What I'm thinking about is I have another tube tester. It does another gas test in it. Well, I'm only assuming there's gas in this tube because it's an assumption. I'm just assuming that. I don't know that there's any gas in it. The test says there isn't any. Why would I doubt what I've done? Because I've never ever found a tube that tests with gas in it. Here's one that would probably test with gas in it for sure. It's got a bit of a hole in the side of it, so this guy would test gas. You see the color of the getter? It's all white. What about this guy? This guy's got no obvious failure in the glass tube, but look at the getter. The getter's completely white on it. Two of them. Two getters. Is this tube going to be gassy? This would be a good one to test because it must be gassy. Why don't we test this one next? It's a 6L6. Let's give this guy a test because all indications are it's full of gas. That way we'll be testing the tester. That's a good idea at this point. Okay, enough for that tube. Oh, wait a minute. It said the EM test was more important for this tube. 1 second here. Forty-three. 43. Up there, yep. 43. Okay, so on the other test now, pull the tube out. Very carefully, out it comes. Okay. Now, I don't want the tube in there while I'm turning all these knobs. I don't know what would happen necessarily. C, G, G, G. No, B, E, B, D. Read it carefully, Jim. B, E, B, D. B, E, B, D, and then there's a number here. We set this to 7. 7. Okay, and then next number is same as it was. 64312, 64312, and 5 with a pile of zeros. 5, and there's the pile. Okay, 43, 22 volts bias setting. Yeah, if you can do this without the tube in there. Bias. Apparently not. Yeah. Well, yeah. Okay, let's put the tube in now. Oh, 25 volts. Ooh, yes, of course, it's the same tube. 25 volts. Same tube back in. Okay. There it is heating up. Now we'll try setting the bias. It's supposed to be 22. Bias is 22. So we're on the 50 scale, which I'm starting to wonder about the switch here. 22 is almost straight up. Hey, what have I done here? What's happened? Is it? What's happened? Meters on bias. Meter on line. Okay, so the meter's working. What's that funny up and down there? Bias. It's just gone. What happened? What am I doing? Are you watching this and yelling at me at this point? This is on test. This is on bias. Oh, wait. Wait a second. Let me read the instructions again there. 22 volts. They didn't put a V on it. Oh, you know what? Yeah, so instead of setting it by the meter reading, you set this by the numbers on the control. You see there's numbers on the control? And my problem is this control is reversed. I replaced this control and it reversed. So I have to figure out where 28 would be. So 28 is normally here. So 28 would be on this side here. So that's 28. That's 28. It's not a question of what's on the meter. I don't do these EM tests ever, but I'm going to do it this time. 43, 22. So now I think we're just reading good and bad. Good. So there you are. That was a long haul to get the meter to say good. So 43 good, no gas. That's the conclusion we can reach here. And we're on to the next tube. That's right, Shadow. Okay, so I am a little bit nervous about testing an obviously defective tube, but I'm just making sure there isn't any obvious crack in it. There's really no obvious reason why this should be gassy. So it's a 6L6. That's a great tube. Too bad it's in the shape it's in. So I've got everything set here, but I'm going to double check now. So we're looking up the list there. 6.3 volts. BGGG. BGGG with anything there. And 26431. 26431. And 0520005200. I'm going to put this in the open position there to start. And goodness knows what's going to happen. I mean, if this is just full of air, I don't really know what's going to happen in here. Hopefully my tube tester can withstand the challenge here. So this will keep the heater off at first. So really, nothing happening until I flip this over. But we want to check for shorts for sure in here. The list shows shorts on 2 and 7. Now we're looking here. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, heater on. Feeder current. That seems to be behaving normally. This is on the 3 amp scale, so it's getting down around a lot. Down around 1.5 amps. Wait a minute, really? 1.5 amps? Is that really what the current is in a tube like this? 6L6. 6L6. 6. CKL. 6L6. Heater current 0.9 amps. Wow, 0.9 amps. 0.9 amps would be, down here on the meter. When I look at that tube, I don't see anything heating up. Darkness here. Okay, so I can feel heat in the tube, but there's no sign of the heater at all. And maybe it's just not visible in this tube. This is light leaking from the light bulb over here. So I'm very nervous about damaging my tube tester too. So we think everything's ready to go. I did the short test. Heater's heated up. Put this back on test. The test result from this test should be 3825. So if we look on the B, on the 20K scale, 38 again. It's way down here. 38, right around where my finger is. Ready? Okay, nothing at all. Nothing. Now, can we test this? Is this tube so shot doing a gas test is bogus too? So I've set it up for the GM test, which is the right test to set it up for. Oh, it says right up there what the filament current should be, 0.9 amps. So to do the test, you were to turn the screen volts to A to reduce it, and then set the bias so the meter's barely upscale. I'm trying to remember this from the top of my head. And you then perform the gas test. Okay, so we go to screen to A. We put it in test mode, use the bias to make the meter just barely come up. That didn't work. This is on test. This is on test. What did I get wrong? Oh, well, the tube doesn't work, so it doesn't work at all. I mean, it failed the GM test, so could be no reading in the GM test, no chance of a gas test working. So what did we learn about this tube? We learned that it draws too much current in the heater. Not a lot too much. Well, yeah, it is still a lot too much because it really should be. Yeah, right down here. It's almost double. Almost double. Well, gets hot. That's about all you can say for that tube. I don't think I have. See, I'm trying to collect these tube testing tubes up here. And I would. Yeah, so this is a totally different tube, but here's the deal with that one. The when they blast the getter onto the inside of the tube here, and this one's up at the top, getter is some chemicals in a ring. They take a strong magnetic field, hold it at the tube briefly during the manufacture, heats the ring up red hot inside the tube, and blasts off the getter material, chemically altering it at the same time and throwing it onto the glass here. Well, that little ring in this tube has come free. It's just flopping around in there. Not going to test it though. Just a different kind of tube failure. Well, I don't have another gassy tube offhand, so unfortunately we can't test the gas test here. How disappointing is that? So we'll just go on to the next tube in the radio. Which one would be next? Let's pull this one out over here. This is the rectifier tube, 25Z5. It's interesting how they constructed it. It's got two sets of plates. When you look at it like this, it looks like just one set of plates, but if I rotate it, you can't really see what's going on in there. Kind of see it, maybe from above. Can't really see, but I'll show you with my hands. So there's two rectifier plates in there, and usually when you have the two of them, they're either like this, but more commonly they're like this in the tube. But in this case, they put them kind of overlapping on a funny angle. They're not like this, and they're not like that. They're like that. What difference does it make? Nothing. Okay. 35Z5. Okay, let me get this guy all set up for 35Z5. What a fun day testing tubes. Okay, let's test the 25Z5 tube. 25Z5. I think that's another rare one myself. 25Z5. So just double checking all the settings now. 25 AEBB2. AEBB with a 2 set there. 60224. 60224. And then 50,000 on the bottom. 50000 on the bottom. Shorts on 1 and 6. Put that like that. Put the tube in. Check for shorts. What was it? 2 and 7? 1 and 6. 1 and 6. So here we go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We're in test mode. I can see the light dim. This thing's drawing current. How much current is it drawing? Okay, so on the 3 amp scale, what's it supposed to draw? 300 milliamps. So that would be full scale on the other setting. 300. You know what? I don't think this is that big. Amps. Well, you know what? That's right in the right ballpark. There's nothing wrong there. Ready for the test. And the value, let's just double bias. We just have to bias? No bias on a tube like this. But we should check the line. Because the tube could be drawing a fair bit. Seems fine. Test. And this is an EM test, so it's good, bad. Sorry, just lost track. Yeah, good, bad. Here we go. In the good. Now, that's one plate, another plate. We get to 6, 4. So we go 0 becomes 4, and 4 becomes 0. 0 becomes 4. 4 becomes 0. Nothing bad happened when I did that. Now we test. Good. She's in the good. Okay, take that tube out of there. Let's Just let it cool off just a touch. It's a hot tube. A hot tube. My rectifiers and power output tubes are hot, and they have a hard job to do. Okay, that's it for that. And the next tube, I'm going to stop for a few minutes here, but let's see what it's going to be. Oh man, that's a tough one to get out. That's a 76. Made in USA, number 76. That'll be in the next tube. These are all fairly rare tubes, I think. So I was just taking a moment here to clean up these dirty tubes, and something interesting showed up. A couple interesting things. One is, this tube is a ballast tube. This is not a regular tube. This is a big resistor, more or less. Something of that sort going on here. And look at this. So I noticed earlier this was a little shorty. I pulled it out. It's a 6SA7 short tube. It has an octal base on it. But this is a radio full of 6-pin tubes. What's going on? When I looked at this closer, and I see that screw there, and I see the screw here. I also see some holes right beside it. A hole there and a hole right there. You can see how the other sockets have been put in. They're put in with rivets. Whoops, I just moved this so you can't see them. There's a rivet right there. So these are riveted in place. But not this tube. The socket's screwed in. And so what I'm wondering, of course, is this an upgrade? Is this a replacement? Something to get a hold of the 8-pin tube that has 8 pins or 7 pins, has a more it's just a better tube, let's put it that way, than its predecessor 6-pin tube. I don't know, who knows, no schematic, we don't know what's going on here. Hey, maybe if I just take a peek underneath, I can tell if this was once something else before it became what it is now. So here it is here. So there's a great big nut and holding it down. So this is a... See, I mean, the pin layout and everything would be... What are you saying? I'm saying there was a different tube in here originally. Out came the tube, out came the socket, in went this socket, in went that tube. That's what I'm trying to figure out, if that really happened or not. This all looks original to me. Just looks original. Okay. If we had a schematic, maybe the whole thing would not be a mystery at all. But with somebody, hey, what happened to the focus here? Come on, what happened to you? Here we go. If somebody was able to do this and do something similar underneath, they had a pretty good idea what they're doing. Look, there's a tie wrap holding this. So that dates this a little bit, using a tie wrap. Not much, but must have been done in at least in the 70s, I would think. Okay, step by step. I'm just trying to make all the observations I can possibly make to make sure I make the ones I have to make. Well, the next tube we're going to test is the 76. Let's set the machine up for the 76 here. 6.3 volts. Okay, we're already set there. E, G, G, G. E, G, G, G. 64125. 64125. Zeros all around. 6 volt bias. 10. GM test is the most valid test. Shorts on 1 and 5, about 1,000. On the meter, the scale we're on is the E scale, or the 3K scale. 3K scale is down here, and the number we're looking for in the end is 76,930. So it's going to be up around this area here. Okay, tube in. Power on. And current flow in the tube. 0.3 amp scale. Too much for the 0.3 amp scale. And the current is actually at 0.3 amps. So it would be full scale, 0.3, 300 full scale, 0.3, it's, yeah, okay. Yeah, that's okay. That's what I'll say about that. Okay, so we've already heated the tube up, but we have to do the short test. And the shorts were on 1 and 5, so here we go. 10, 9, 8, 7, 6, 5, 4, 3, flash doesn't matter, 2, 1. And we're back to heating the tube. Bias setting for this tube is 6 volts. 6 volts on the 10 scale. 6 volts up here, about like that. Something wrong with my scale switch here, isn't there? My gosh. Okay, we'll leave it on 10. Go back, we'll check the line quickly. It's fine. Back to test. Get ready to do the test. I already figured out where it was supposed to be on the dial. Up around here. Test. Right there. She's a winner. That's actually the reject point. That's the bottom, where it's got to be at least that amount. At least 930. And if we read this really carefully, we're on the 3K scale. Okay, read this very carefully. 3K scale, so 3 is right there. And expectation is 900, and that would be just right 930 right here. So that, you know, as accurate as this is, that's dead on 930. That's that's what it looks like to me. A little bit of parallax in the camera there, maybe. Pretty darn close, though. Good enough. Good enough. Tube test good. Now, why wouldn't we do a gas test? Because I'm not smart enough to do it. So first thing was move the screen to A. Adjust the bias control during tests so the meter is just barely up. Can't do it. Can't get there. I think it said something about if you can't get there, you go to B. Still can't get there. Oh, something funny going on here with this tube. Back to A. I can't get it down here to do the test. I'm probably doing something wrong. Let's not worry about gas. The tube test's okay. The 76. This is a. These are not very. These are not very valuable tubes. I'm surprised that you can get these for like 20 bucks on the internet, just from here in Ontario. I would have thought they're more expensive. Now, of course, it costs a little bit of money to mail them. So 20 quickly becomes 50. contacts and everything else. So far so good though. Haven't found a dud yet. Okay, let's go to the next one. We're not likely to find a dud here. Oh, so this is the ballast tube. Have a look at this. Just looking at it under the close-up camera here, trying anyway. There, see what's inside it? A bunch of springs. So those are all heating elements, or heat dissipating elements. 165R8. What are they doing with this in the radio? They're throwing away a lot of heat here. Sometimes these are in the tube heater string, but these aren't strung together. Are they? No. These, well, let's find out a little more about this. 165R8. 165R8. Of course, I've never heard of that. 165. Is that going to be in here? 117. 183. There's no 165. Maybe they put ballast tubes in a special spot in this book. Would they? Could I ever find it? Power tubes, camera tubes, photo tubes, vibratrons, ignitrons. I've never heard of an ignitron. Ignitron. I mean, there's special types. Traveling wave tubes, klystrons. Well, I don't see it listed here. Iconoscopes, monoscopes, videocons, image orthicons. I don't think any of those are of any interest to anybody anymore. Well, no. Okay, next source. To the internet. So here's what Radio Museum has to say about this tube. They call it a current regulator. Erdox with, what is that? Iron hydrate? What is that? What is that? I don't know what that is. Current regulator, so they don't call it a ballast tube here. They don't say much about what it's used for here. So, the ballast tube handbook. I don't have one of those. Not much more on it here. See what else we can find. A 160 kb is a different tube. Is a ballast tube that drops 48 volts at 300 milliamps. So 300 milliamps is suspicious. That's a typical current heater current, tube heater current. It would have been used in series with filaments of a radio. Should have a resistance between these three pins. Yeah. There's the kind of radio it's in. Hytron current regulator tube. 165R8. That's my tube. Could consider 165R8 to be about the same, drops 49 volts at 300 milliamps. It just sounds like a big resistor. 49 volts at 300 milliamps. If I had a schematic, we could see where they have it in the circuit. Otherwise, I got to look through the back of the radio, 1938, and sort out. So let's make an assumption. This guy is in series with the heaters, and it's just a voltage dropper. So how does that make sense? Well, you know, there's no way I can test this tube, and there's no real need to. If this is in series with the other tube heaters and the tubes heat up, then this must be good in the sense that it's conducting current. Can't imagine other than reading the resistance between the pins, and how would that go out anyway? I mean, this thing's going to be good, or it's going to be open. I think that's kind of how these would go. So I'm going to put that back in. It's an unusual. Well, in other radios where they're trying to drop some of the voltage in the heater string, all they simply do is stick a high wattage resistor down under the radio. But I guess in this case, it'd be dissipating too much heat, so they put the hot thing up on top in a glass tube. Okay, well, the next one would be this one then. We'll do the 8-pin octal 6SA7. So probably this radio was originally designed with a 6A7, which would have a grid cap on it, and then that tube was replaced by this tube, the single-ended, the S-type, 6S, S single-ended type. Who knows? So I'll get this set up for a 6SA7 now. I'm just going to leave the camera running. You know, you're looking for things to do today, watch me. That's what you can do today. 6, or way too high here. 6, way down there. 6SA7. 6SA7, here it is. Let's put it right there. Okay. 6SA7, 6.3 volts. BGAG. BGAG. And then 06432 06432, and then 25100 25100 0. Oh, wait a minute, I slipped. Whoop, wrong tube. Start over. My eye slipped there. BGAG 06432 06432, correct. 25100. Well, no wonder my eye slipped. It's the same numbers on another tube. 25100. Okay, 6SA7, 0 volt bias. I guess it's right here. Expected reading is 775. Bias 2.7. Whoops, that's not right. That's shorts on 2 and 7. There is no bias. Shorts on 2 and 7. It's a GM test. We're ready. We are ready. 6. Away we go. This guy's current is a 300 milliamp tube. Testing the amplifier portion of the tube. Okay, got the heater on, but heater off. Shorts on 2 and 7. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Heater's back on. Heater current flow. Oh, I can't do it. Can't really test it well because of my sticky meter. But all looks normal. Isn't there a bias setting on this? 0 volts. Let's check it. Yeah. 0. Line for fun. Now that's fun. Now that's what I call fun. Fun? Wow. Here we go. And what's it supposed to be before I go with it? It's supposed to 775, and we're on the 20 scale. 20 scale. It's either way down here or it's up here. It's way down here. This is a crazy tube tester in this respect. A lot of the readings are right on the edge of the meter. 775. How are we going to read 775 on that? 775. Okay, and the scale we're on again, we're on the 20K scale, which is the top scale, 20. 775 on 20. So that's just above, I would say that's above 500. About 600 on that meter. 0 is low. The meter 0 is a little bit low. So we could assume it would go a touch higher. I think it's hitting it right on. That's what I think it's doing. I think that one's dead on. Okay, next test for this one, if we wanted to do it, oh, we need to do it. There's diodes in here. Next test. Next test is an EM test. We don't need to do it. Then we have 3 more tests after that. That's what we want to do. FEBB 20. FEBB. FEBB. I'm watching to see if my tester goes nuts. I left the tube in, and in some testers you can't leave the tube in while you do all this. In others you certainly can. I don't know about this one. We'll find out the hard way here. 21. 21, so we set it right on the numbers here. 21 is like that. 21. Just lost my track of where I am on that. So just this is a difficult tester to use because they got the numbers all stacked up here. It's so easy to get it wrong. 06432, what it should be right now. 06432. Okay, and the next number is 251, same thing what it should be. 25100. And then we have 8. I want to set this number here to 8. So 8 would be over here, but the control is backwards. So 8 is about here. I'm doing an EM test on the amplifier. That's not what I wanted to do. Oh, I see. Oh, I read this wrong. I think my eyes popped to the wrong spot for a moment. So it shows the 2 important GM tests first, and I've skipped the second GM test. Let's go back and do it on the oscillator. It's all we really need to do. B, G, G, G. Okay, back we go. Back we go. B, G, G, G. 06041. 06041. 25200. I think these are the heater settings, and you shouldn't have it in there. 25200. Frankly, I'm not sure. Should read the manual more carefully. 0 volts on the bias control. 0 is going to be something like that. Oscillator, GM test, short same place, and in this case 2850, and this time we're on the same scale, 2850, so that's going to be up like this. 2850. Shorts first. 7, 2, bias should be on 0. There it is, pretty much on 0. Test position, ready for the test. Up we go. There it is. If you notice that, I don't know if you can see that the pointer came up and then drifted downwards. And sometimes I think that's an indication of a weak tube. So the actual number there, 2500. 25. 25, and it's supposed to be 2850. Now how's that compared to 2850? I'd switch cameras for you, but it's a big hassle in my shop here. Let's try that again. 2850. Well, that's really close actually, because that'd be 3,000 there. That's really, really close. 2850. She's good on both accounts. Good on both accounts. That would be the. I only did one. Did I do one diode? No, good. Amplifier, oscillator. That's good. That's good. That's good. No diodes. No diodes, Jim. That's another tube. So the last tube to do now is the guy who's wearing armor. He's got quite the armor here. GOAT. It says GOAT. G-O-A-T. GOAT. New York. Patent pending. They put a patent on this. Okay, so there's a holding ring right here. So just pull it down. Slide it off. Wow, look at that. It's got writing on it. Okay. This is a pretty old tube, I think. It says on here, the Mitchell Radio Service, 69 Oak Hill View, Rochester, New York. G General 1745. I don't know what that is. Here we are. Date tested. Poor, fair, good. Date sold. There's the date sold. You can read right on here. Looks like a little hard to tell. 1946. Well, the reason the date is on here is because tubes were very unreliable. Now you go buy a tube from a tube seller, bring it home, and a week later it's failed. And you're going to go back to the tube seller and say, hey, you told me this tube and now it's failed. And he goes, yeah, I remember you. You came in a year ago. That tube's a year old. No, I came in last week. That tube's only a week old. I want my money back. Blah, blah, blah. So they started putting dates on the tubes when they sold them. So when you return to the seller with your defective tube, he would kind of look at how long it ran and then maybe discount the price on the new one if this one failed too soon. Stuff like that was going on. That's how unreliable these things were. 6D6. Made in the USA. RCA. Okay, 6D6. That's the guy we're going to test. Let's just keep it rolling. Let's keep it rolling. 6D6. 6D6, there it is. Okay, 6.3 volts. EGGG. EGGG. This control doesn't matter. Next row, 64322. 64322. 64322. And then 50010. 50010. 3.2 bias, GM about 1,000. Shorts on 1 and 6. Grid cap. Uh-oh, I have to put on the grid cap. Okay, so there's a grid cap thing here, and I have a grid cap. I have a grid cap in my other tube tester. Okay. I don't know if this is going to fit. Let's see. This is for a big cap. Come on back up here. Wow, it's not big enough. Okay, so we got the right heater here. Now, I bother with a proper grid cap, or just there. Get a clip lead. Oh, clip it on a grid cap. That's a great big cap. How's that going to clip on there? I need like a great big clip. Or I need another cap. He says, somewhat yelling in the microphone. Okay, clearly I have to go hunting for stuff here, so I'm going to stop for a sec. Okay, found myself a grid cap. And then we'll just use a clip lead. What did I do with it? What do I have to do here? That's going to do the trick. Grid. It's definitely grid. G cap. Yeah, definitely. Grid cap. 6D6. I think we're all set. Shorts are on 1 and 6. There we go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Back on the heater. Quick check of the heater current. Oh, I can't seem to check it very good. It seems a little high. That would be around the 3 amp scale. That's like 400. I don't know what the current's supposed to be. Let's not worry about it. Bias setting was supposed to be 3.2 volts. Bias setting 3.2 volts. That'll be something like it there. 3.2 volts. Line check. Touch low. There we go. Ready in the test mode. And what is the test result supposed to be? 1000. And we're reading on the 3K scale. The 3 scales down here. 1000. Right there. Hit it. Right above. Fantastic. Could do an EM test, but no reason. It passed the test. Let's just check how sensitive this bias control is. Put this on again, and we'll wiggle this. So that does make a lot of difference. Yeah, we can be quite wrong with this. In this case, quite wrong with that. We're good. We're good. That off there. Pull this out of here. Go to the side. What's left? We've tested all the tubes. And they've all tested okay. A little bit disappointing. There's something wrong with this radio, and I was hoping it would be one of these. In a way. They don't have a lot of replacements of this vintage of tube. So there's a good chance I have no replacements for some of these. Especially that ballast tube. I don't think there's a lot of those kicking around. So put this guy, we'll have to put his clothes back on here. Now this is coming over from here, so we want the slot like that, and we want want the big pins. This is actually right around the wrong way. I'll rotate this a bit. Actually, it's easy to rotate. So we'll just put it in and rotate it as we need it. It's perfect. Cap on. If you look at that shield, I see how the metal shield comes right up this high. Now that's kind of inconvenient. They had to cut a slot in it to fit this in. Well, why would they bring this collar up this high? Because it's still having an effect, I guess. It's still up here, it's still shielding. Maybe the cap is shielded, and the wire here is in the clear, just in this area here. Maybe that's why they do that. I don't know. Maybe the guy who designed it thought it looked really cool if it went up like that. Or maybe they could sell more of them. Look at mine. Patented. It's got a name on it. What's so good about his? High collar. That's why he's selling them back then. My high collar tube shields. Oh, I make up a lot of stories, don't I? So, what's the story now with this radio? Phew, I don't know what to do next, except to think about it some more. Maybe we turn it on, do a little signal tracing in it, something like that. I don't know. I gotta think about it. I have no schematic. I don't know how I'm gonna get through this. I really don't. But thanks a lot for watching, and tomorrow I'll figure something out to do.